Hi, Assalamualaikum and a very good morning. So today we'll be doing some reinforcement exercise that consists of subtopic of 4.1 until 4.3. I will first show you one of the example of the question, and then you will proceed doing the other example by your own. You can discuss that in group, but please do it individually. This is to develop your confidence, and if you can do it by your own without any much help from others, it means that you are on the right track in understanding this subtopic. Without any further ado, let's start. So, I will do the first question here. So my molecule is CS2. So in the first step, I need to draw the most plausible Lewis structure for the CS2 molecule. So what I need to do is to count the total number of valence electron. Carbon have 4 electrons. Meanwhile, sulfur, in where I have 2 sulfur, I will have 6 valence electron multiplied by 2, where I have 12 electrons. So the total number of electrons that I have is 16 electrons. Now, in determining in drawing the Lewis structure, I need to know which of the atom gonna be the central atom. So I will choose the most electropositive atom, which is carbon, to become the central atom. So carbon gonna be the central atom, and it is bonded with 2 sulfur. One bonding pair represents 2 electrons, so I have 2 bonding pairs here. Therefore, I minus 4 electrons. The balance that I have is 12 electrons. The 12 electron will be used to fill up the terminal atom so that it is octet. So let's do that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I've used up all the 12 electrons and there's no balance left. However, as what you can see here, the structure is not octet. The carbon need to have 8 electrons in order for it to be stable. Therefore, we need to bring the lone pairs from the terminal atom into the central atom so that the formal charge gets lower, and it is so that we can form a much more stable structure. So let's bring the formal charge, let's bring the lone pair from the terminal atom into the central atom. You can choose any lone pairs from the terminal atom, but for me, I will choose here and into here. From the single bond, it become a double bond. Same goes to this side. From a lone pair electron of sulfur, I bring it to the middle. Hence, this single bond will form another bond in order to become double bond. So, the final structure that I will get is carbon, sulfur, sulfur, 1, 2, 3, 4, and then because of the 2 electrons has been transferred to the middle, and hence I will get another bond. And same goes to here, therefore I will get another bond. The first bond is sigma bond. The next one will be pi bond. Sigma bond and also pi bond. Now, let's count the formal charge in order to ensure that we got the lowest formal charge in the molecule. Let's say I count for carbon. Carbon has 4 valence electrons multiplied by 1 minus 1, 2, 3, 4 bonding pairs. And I need to also deduct the lone pair electrons, but there's no lone pair electrons surrounding the carbon, so I make it 0. So the total formal charge at carbon is 0. Next, I need to count the formal charge of one of the sulfur atom. So I can just choose any one because it is similar. So let's say I choose here. So sulfur, the valence electron is 6 minus with 1, 2 bonding pairs, minus lone pair electron. So I need to count one by one. 1, 2, 3, 4. Hence, I will get 0 here. So the formal charge at carbon is 0. Sulfur is also 0. When you know that, you get the lowest formal charge, which is closest to 0. You know that a plausible wave structure has been correctly drawn. Now, from your drawing, you go to the step number 2, where you need to predict the molecular geometry shape using the VSEPR theory, which is valence shell electron pair repulsion theory. So from the structure that you have drawn, which is like this, you need to determine the number of the bonding pair electron. So for this structure, you have 1 and 2 bonding pairs, because double bond will be considered one bond in determining the bonding pair electron. So 1 and 2 bonding pairs. Is there any lone pair here? No, there isn't lone pair. There is no lone pair at the central atom. So the lone pair electron is going to be 0. Hence, the class of the molecule going to be AB2, where the basic shape is linear. At the same time, the molecular shape will also be the same, which is AB2, and molecular shape is linear, because there is no bonding pairs that were changed into lone pairs. And the molecular geometry is still the same as before, and the bond angle gonna be 180 degrees. Now, we proceed with step number 3, which is we need to explain the polarity of the bonds and the molecule. So let's draw the structure once again. C, double bond S, double bond S. Okay. In this structure, there are 2 bonding pairs and 0 lone pairs electron. Between sulfur and carbon, we know that sulfur is a much more electronegative atom. So, since sulfur is more electronegative than carbon, all the CS bond are polar bond. We know that this region, the electron density will move towards sulfur. So, I will draw it there. Since sulfur is more electronegative than carbon, the electron density will move towards sulfur. And same goes to this side. So we can say that the dipole moment are arranged symmetrically. Hence, all the dipole moment can cancel out each other, because you can imagine that the bond dipole going to the right hand side to be 10 Newton, and at the same time the bond dipole that goes to the left hand side is also 10 Newton. So 10 Newton right hand side, 10 Newton left hand side, so it can cancel out. Hence you can say that the resultant dipole moment is equal to 0. So mu is equal to 0. Hence, CS2 is a non-polar molecule, because this one can cancel out. Can cancel out and cancel out. Next, I go to the next step, which is I need to identify the type of hybridization at the central atom. So as you know, the bonding pair electrons that we have is 2, and there's no lone pair electron. So the total number of electron pairs that we have, which is this one plus this one, we're going to have 2. Thus, the type of hybrid of the central atom is sp. Because you know that S plus P going to produce 2sp. So this one refers to the bonding pairs. So when the electron pairs is 2, hence the type of hybrid will going to be sp. Okay. Now you need to draw the orbital diagram for the central and the terminal atom. So your central atom is carbon. So carbon has 6 electrons. Hence, its electronic configuration gonna be 1s2, 2s2, 2p2. Since we are studying about the valence bond theory, so we only focus on the valence electron, where the valence electron is the electron that involved in the formation of bonding. So let's do that. At the ground state, they have 2s orbital and 2p orbital with a electron of 2s2 and 2p2. 2s2 and 2p2. Okay. Now, at the excited state, you need to bring one electron from the 2s orbital into the unoccupied 2p orbital. So that it's gonna be like this, like this, like this, and like this. We turn the arrow because we need to follow the Hans rule. It needs to be paired singly first before it is being paired. And why do we do this? This is because two of the electrons, single electrons, will be used to form sigma bonding, and two of the electrons will be used to form pi bonding. Hence, in the hybrid state, we will only combine these two orbitals and left these two orbitals to make pi bonding. So, when we combine one s orbital with one p orbital, we will get sp orbital. But we don't get one sp, but we got two sp orbital, as what I shown here. So I write here, I write here, and then the 2p orbital that is left unhybridized is left unhybridized, and it has two single electron as well. These will form sigma bonding. The unhybridized orbital will form pi bonding. Now, we need to draw the terminal atom, where the terminal atom is sulfur. So, sulfur. Okay, sulfur have 16 electrons. So the electronic configuration gonna be 1s2, 2s2, 2p6, 3s2, and 3p4. Correct? So I'm gonna focus on the valence electron only. So I have 3s2 and 3p4. Okay. So the terminal atom gonna have this kind of electronic configuration. So you can imagine that I have 2 sulfur, so I can multiply it by 2. However, in exam, you can only write this, you can just write it one time. But for your understanding now, you can imagine it has two of the same electronic configuration, because you have 2 sulfur atom. So one sulfur atom, you have 2 single pair electron. When you have 2 sulfur terminal atom, you're gonna have 4 electron pairs. So 2 will be used to make sp bonding, and the other 2 will be used to make pi bonding. So now let's draw the orbital overlapping. So the carbon atom gonna be the central atom. So it has the hybrid orbital of sp. So it has 2 of them. So 1 and 2, sp and sp. It will overlap with sulfur, two of the sulfur, one from the right hand side and the other one from the left hand side. So let's draw sulfur atom, and then it will overlap with sp hybrid orbital, and here it will also overlap with sp hybrid orbital. This overlapping will produce sigma bond. At the same time, sulfur also have another hybrid orbital, unhybrid orbital, where it can use to form pi bonding. So the 2p orbital that came from sulfur can also make bonding with the unhybridized carbon atom, which is from the 2p orbital as well. So I can also draw it here. So this kind of overlapping, which is side-to-side overlapping, will form a pi bond. And I will draw it shaded region showing that it is a pi bond. And before I forget, the sulfur here, you also need to mention its orbital because it came from the 3p orbital, so we have to mention that it comes from the 3p orbital. At the same time, another sulfur also have unpaired electron. And this unpaired electron will then combine with the carbon hybrid orbital, which is with this one. So I need to draw another one. So this will also form a pi bond. Okay, as what you can see, if I were to compare that with the Lewis structure, the orbital overlapping will be consistent to my Lewis structure, where I get C double bond S and C double bond S. One will be used to form sigma bond, and on the right hand side, one also will be used to form a sigma bond. The other bonds that they were making is a pi bond, where on the right hand side it is labeled with a yellow color, and on the left hand side it is labeled with orange color. So it is consistent to my shape. So there are 1, 2, 3, 4 bonding at the central atom. So if we were to describe the formation of bond by involving the overlapping of hybrid orbital, we're gonna answer this in terms of writing. So hybridization on carbon is sp hybrid orbital, right? So the sp hybrid orbital of carbon will overlap with 3p orbital of sulfur to form a sigma bond, which is here. At the same time, another sp hybrid orbital of carbon will also overlap with 3p orbital of sulfur to make another sigma bond, because we have two sigma bond. At the same time, the sp unhybrid orbital of carbon will overlap with the 3p orbital of sulfur to form a pi bond, because the pi bond were made from the unhybridized orbital. So we need to write unhybrid orbital here. So this goes for the left hand side, and the same goes to the right hand side, where the sp unhybrid orbital of carbon will overlap with 3p orbital of sulfur to make another pi bond. So I will indicate this by using a orange label to show that the pi formation happens at the left hand side, and a yellow label to show that the pi bonding is made from the right hand side. The structure is consistent with the Lewis structure that I have formed from the beginning. So I think that's all from me, and this is quite a complex example because you don't usually deal with pi bonding. So I hope that this is going to be the first to give you some idea on how pi bonding is made, and from that you can try yourself to do all the other exercises that is left in the boxer sheet. So that's all from me, and good luck doing the other exercise. Thank you and goodbye.